if I brought some frogs in this room at the beginning of the lecture and I placed them here, by now they would be all around. So as a function of time, we can see diffusion of actually everything. So the next thing to look at it is the topic of the currents that we have, the last component from the continuum equation, so the charge transport in semiconductor. We can consider two cases, the lattice scattering and the impurity scattering. And this is the phenomenon that influences the movement of the electron, which is passing in the electric fields, for example, or even without electric field, we still have the thermal movement of electrons. And this effect of lattice scattering, it will dominate at high temperatures. So there will be collisions between the electron and the crystal because of the movements of the lattice. And the higher the temperature, this amplitude will be higher and the probability of collision will be also higher. So this is the increasing with high temperatures, and this will influence also the conductivity as a function of the temperature. At high temperatures, this will be the dominant effect. The second effect is the impurity scattering. Impurity, it can be a dopant atom or some really unintended impurity. And these dopant atoms, they will have a different charge than all the other atoms in the lattice because they gave extra electron away or extra hole away. So they will be positively or negatively charged. And because of that, there will be Coulomb forces that in addition attract or repel the electrons and can contribute to additional deflection of the movement of the electrons. And this will especially dominate maybe at lower temperatures, at lower electric fields, so generally where the electrons are moving more slower. For the case where we have no electric field applied, we have to remember that electrons in the conduction band or the holes in the valence bands, because it's also about them. So they are moving all the time. So if we look at the position x, y, at any point in time, then there will be the collisions, and after the collision, the direction of the movement changes. It's similar when we apply the electric field. There is still some random component to that, but the tendency will be for the electron to move into one direction of the electric field, the hole into the negative side of the electric field. So there will be some net effect. And the same thing, let's say the electric field is applied in just the x direction, and the y we forget, it's something random. For the x direction, we can look as a function of time. So any next time step that we analyze, let's say here we have the x position and the time, and as a function of time, the charge carrier will be moving maybe a bit backwards, but the tendency is to move forwards. There is this random component, but still this kind of behavior we can describe with statistics, for example, by a mean velocity. So from these three equations, which describe the force on the electron with acceleration at certain effective mass, then where the acceleration is the drift velocity, so the average velocity over a certain time, and Q times E is what we actually get as a force in the electric field. So from these three expressions, we can define what actually this drift velocity is. It's not any instant of time where this is defined, but this is just the average. And there is the relationship between the velocity and the electric field. And that's what we are interested in to describe mobility. So it will be the time times Q divided by effective mass. And exactly this, I'm repeating on the next slide, in the bold, this is what is called mobility. So this is the relation between the drift velocity and the applied electric field. With Tc, the average time between collisions, effective mass of charge carrier, so it will be different for hole and for electron. With the same electric field, that will be a major difference. And especially so for holes, they have higher effective mass, so the mobility is typically much worse. What we have to know about mobility is that it's changing with applied electric field. Well, the conductivity will be changing with temperature, but the average time between collisions, of course, it will be depending on the temperature. And the scattering effects that were shown before. So these exactly are the effects that influence the Tc, the time between collisions. So now let's consider a piece of semiconductor with an applied electric field. We have certain surface, that is our reference surface. We can see how many holes and how many electrons cross this surface per unit of time. So we will have the drift current defined by that, by looking at how many charge carriers cross this surface per unit time. And this results in the description of the drift current for holes and for electrons. And this we can express as the charge times the number of those charge carriers per cubic centimeters times the drift velocity. So if we remember that the mobility is the relation between the drift velocity and electric field, we can describe these current densities for drift current with using the mobility. And mobility is useful even for us for calculations, for some hand calculations or even understanding, because we have it available in the physics tables. We can look up for which material at which temperature what is the mobility, and also for holes and electrons there will be always separate number. So then the total drift current, when we include the mobility effect, is the electric field times the multiplication of the mobility and the density of charge carriers. We have and electrons and holes, so both have to be taken into account. From the relationship between the current and electric field, we can define the conductivity of the material. And conductivity is now described by this, what we have here in brackets, and is in the units of 1/ohm times centimeter, or scaled to millimeters or meters. So it also depends what is useful for us, we can recalculate. So let's have a look at some values of mobilities of different materials. For silicon, germanium, gallium arsenide, and another compound semiconductor, cadmium telluride. So the mobility of electrons, the typical tendency is that electrons have always higher mobility, and that's because of the effective mass. In silicon, for holes, it's about 3 times lower. Because of that, as a rule of thumb, if some of you already have attended the lectures on chip design and you design an inverter with MOSFET transistor, P-channel MOSFET we always make twice as large than the N-channel MOSFET in the same structure. If we want to have the conductivity the same for P side and for N side, we need to appropriately scale to compensate for this difference in the mobility of charge carriers. What is interesting is this gallium arsenide and cadmium telluride. So cadmium telluride, at least mostly what I know, it's for solar cells or for detectors, and there we will especially exploit the high mobility of electrons. And the holes, they are rather an obstacle because we just have to wait until they recombine or get to the place where we measure them. They take much longer time. For gallium arsenide, the high mobility of electrons, it helps us with having high-speed devices, and always there will be MOSFET devices, so many based on the electron conductivity. So we don't have this complementary, it's not useful to have the complementary gallium arsenide devices. So taking all the different effects, when we look at the conductivity as a function of the temperature, where the temperature increases into this direction, we have the different regions. We have those. We have to match the A, B, C, D to the different regions. So it's thermal generation, impurity scattering, freeze out, lattice scattering. Some of them maybe I didn't quite explain, but I think that you can imagine what that could be. So region A, what it will be? It's the lowest temperature. It's freeze out, yes. So the charge carriers are frozen. So basically they are just starting to get into the other band, conduction or valence. Then at B, or let's start with D. That may be the easiest. What is D? Thermal generation, right. So at very high temperatures, this is the dominant effect because we saw this exponentially increasing concentration of charge carriers. So now between B and C, can you guess which one is which? B, what will be B?
Impurity scattering.
And impurity scattering, and why?
Because first we said that lattice scattering is more important at high temperatures.
That's right. So at high temperatures, the lattice scattering dominates. So that's by elimination, it should be like that. So the conductivity has a bit of a roller coaster curve. We will have sometimes we can benefit of this effect of decreasing conductivity and then increasing again. For example, when we are looking to have several components that are matched with it, so several parallel components like in ESD devices, and we would like that they all get similar conduction. So one is heating more, but then it reduces conductivity and gives chance to the other parallel components to catch up and take more current, and there is some balance thanks to that. So just knowing that, it's not theoretical, really you can use this information when designing your devices. So we had drift current. The next part is diffusion. If I brought some frogs in this room at the beginning of the lecture and I placed them here, by now they would be all around. So as a function of time, we can see diffusion of actually everything to be more equally distributed in space. Of course, if we assume that there is no electric field, or in case of frogs, if there was a pond at the other end, then maybe that would have some overall weight on the final distribution. But what we can see that they will tend to distribute into the uniform situation. So the same thing happens with charge carriers. If we have, for example, a spotlight emitted onto the semiconductor, and we have very localized generation of charge carriers, then remove the light. Something that happens is, of course, is the recombination. But whatever is faster, we have to look at the mobility, at the total number of those charge carriers. But even though they are, the concentration is decaying because of the recombination, but also they are diffusing. Similar thing happens when we have photodetectors. There will be a, let's say, photon hitting semiconductor, leading to charge carriers generation. And then we have applied electric field between two plates of the detector, because as the charge moves across the detector, then during this movement, we are receiving the signal that we can read out. And imagine that we have a matrix of for pixelated detector where we would like to make an image. And there we hit an obstacle, because as this cloud of electrons is moving towards the electrode, it's also diffusing. So hopefully there is no recombination. We don't want to lose them. So hopefully electrons go in one direction and holes in the other. And once that happens, and the detector is, let's say, at low temperature, so there is no other charge carriers that can recombine, still what happens, we will have the diffusion, and in the end, we might read the signal on several pixels. So it's also an effect that in many situations we have to consider. And now this diffusion is described with a diffusion constant. And this diffusion constant is dependent on the temperature. The higher the temperature, we will have the higher diffusion constant, so we can imagine it happens that the carriers spread faster. And also, again, we have mobility. So we can use the knowledge that we learned from the drift current. There is the mobility, but it's exactly the same parameter that we have here in case of diffusion current. And diffusion, just if we want to describe in a single dimension, we can still see what happens in the equation. We have the minus sign, the electron or the unit charge of electron or hole, diffusion constant, and the change of the charge carrier concentration over time, so time and position dependent over certain distance. In case of 3D, we have a divergency operator. It looks simpler. No, it's much shorter. Where else we have diffusion? I already mentioned the photodetectors. We have also p-n junction. That's another case where we will have to consider diffusion. In fact, you might think it's a bit crazy, but we will discuss it in one of the next lectures. In the forward directions, when there is forward biasing of the diode, it's the diffusion current that dominates. Many people think intuitively that we apply electric field, so it will be drift current, but no, it's the diffusion. So it's a really significant effect. We have large number of charge carriers, and even if some small fraction of them diffuses, it can already have very important contribution. So what we have here is, in the p-n junction, we have the p-type and n-type. That means that we have different types of dopants. On the n-type side, those that give more electrons and leave negatively charged ions inside, and on the p side, those that give contribute holes to the valence band and leave negatively charged ions. So we will have the more electrons on the n side and more holes on the p side, and then they will start diffusing. So we will have the diffusion current. Of course, because of that, we start having electric field, and then there will be balance and space charge region. But this we can discuss later. Here, it's important thing that it's another place where we have the diffusions. Another just keyword I would like to mention here is the lifetime of charge carriers. So we will have the minority carriers diffusing into the other side of the semiconductor, and the recombination will be quite significant because it's an electron surrounded by holes, so very soon this recombination also happens. Which means there is, again, no electron, so the diffusion will be the continuous process. So for the minority carrier lifetime, we have the inequality between the recombination and generation. That means we will have also those minority carriers. And the lifetime describes the decay of the concentration. So the concentration of the dopant atoms in p-type or n-type times recombination constant, which is temperature dependent. And then lifetime increases with decreasing temperature, with decreasing number of defects. So if there are also some defects in the semiconductor, it's more probable that they will recombine, so that the lifetime will be shorter. If the temperature is higher, then there is higher intrinsic charge carrier concentration, so again, it's higher probability of recombination, so the lifetime is again shorter. So very often we don't want recombination. So for example, in bipolar transistors. As the charge carrier, we have the emitter, base, and collector. And the charge carrier, we would like that it goes from emitter to the collector without recombining in the base, because that's the higher base current, lower gain. It's less efficient device. So we don't want that, for example, in the base of the bipolar transistor. In solar cells, we also don't want the recombination because we want the charge carrier to travel as far as possible and to give as high efficiency as possible. And similarly, in photodetectors, we don't want recombination because then there is loss of signal. If immediately after interaction there is recombination, then part of the charge, so part of the energy of the photon we are not reading, so it's lost. But if we want to have a high-speed switches, we have a switch conducting, then we switch it off, and there are still some charge carriers that didn't recombine, then we want to get rid of them. We want this to happen faster. So it depends on the case what we might see as good or bad in terms of the minority carriers' lifetime. What is next I would like to do is to combine what we know already, those two types of currents. It's really trivial, but that gives us the total current density. And in semiconductor, we will have always, almost always, as soon as we have electric fields, we will have end, drift, and diffusion currents. And even if we don't have external electric fields, we might have electric fields internally. So the total carrier density for electrons and holes respectively is the sum of the drift current, which happens in the presence of the electric field, whether external or internal, and diffusion, very much temperature dependent. In both cases, mobility is here. In the diffusion current is hidden under the diffusion constant. In the drift current, we see it quite easily. And if you remember this continuity equation, which describes the charge carrier concentration over time, dependent on the generation and on the recombination, then we also have the component related to the current density. So if we place there our equations with the drift and diffusion current density, we already have a set of equations describing the charge carrier's density over time and taking into account the charge transport modes that can happen, the drift, transport, or diffusion. And if in addition we add the Poisson equation, then we have a set of equations to solve any problems. So these are the equations that are, for example, used by CAD tools where, for example, Centaurus TCAD, where we have to solve the charge carrier concentration as a function of time in the space. And these are the equations that are implemented behind the user interface that you are using. So what is to remember is the relation with the conductivity between the charge carrier concentration that gives us mobility, and the charge carrier concentration is also hidden in the current. So everything is quite strongly related. And I think that it pretty much covers the topic of the conductivity of semiconductor I wanted to prepare for today. So one more thing that we can also add is in the 3 dimensions. So we will have a divergency of currents, then everything is a bit more complicated than it's definitely not for solving diode equations in 1 dimension, but 3D. Very often what might be useful also for you when you analyze the operation of the devices is this terminology of steady state and thermal equilibrium. So in the steady state, the charge carrier concentration over time is not changing. In thermal equilibrium, there is a small difference. The charge carrier concentration over time is also not changing. But in addition, we will have, for example, no external photon emission that generates additional charge carriers. So the generation recombination rates they are equal. And also the current density in the, let's say, surface considered is 0. What we had today is the band model, where it comes from. And with that, with this background, the most important takeaway is the fact that the charge carriers, they need certain energy to move from conduction to the valence band. And it strongly depends on the temperature, it strongly depends on the material type. So that gives you an overview why we have different materials for different applications. And then for the conductivity, we have two components. We have the number of charge carriers, which we have the two subcomponents, the number of available states to occupy the charge carrier and the probability related to the Fermi-Dirac distribution, but we use Boltzmann approximation. And the second part to conductivity is the mobility. And mobility won't be always constant, especially at high electric fields. It will change also with temperature. It's different for different types of charge carriers. But with that, coming back to the table at the very beginning, the conductivity of charge carriers, now you understand it was given at certain temperature because we saw the roller coaster curve for the conductivity, but especially at high temperatures, it's increasing conductivity with increasing temperature. So the resistivity coefficient is negative. And for metals, you might still wonder, okay, so it was positive. So we have those scattering effects that actually are there, but we have no more additional charge carriers. So we are just left with that. Thanks for coming. I hope you don't mind having a few more minutes for coffee before the next plan in your schedule. Have a nice weekend.
You're the signal in my static hum, a perfect match we've overcome. Wires crossed, but we still